All right, guys, I'm just going to go through a bunch of examples from Chapter 8 in the hopes that you will understand all this better and do well in your test. So starting with 8.1. 8.1 was all of the factoring, canceling, multiplying, dividing, all of that good stuff. So I'm going to do examples that cover kind of lots of different instances of factoring and then one multiplication, one division problem. So first one is this. Okay, so this is a multiplication problem. Anytime you're doing one of these, what you want to do is take a look at every single piece, factor it down as much as you possibly can. So over the next couple problems, I'm going to cover basically any factoring technique that you could see on the test. So start with the upper left here, x squared plus 5x plus 4. That's one of those simple trinomials, so you're just going to start with two different sets of parentheses. You know you're going to have x times x to give you this x squared, and then these two pieces right here, they should be multiplying to 4 and adding to 5. So that would be a positive 4 and a positive 1. Okay, and then we're basically doing the same sort of technique with the one right underneath it. So start with your two sets of parentheses. X times x gives us this x squared. We want to multiply to 1 and add to 2. So that would be a positive 1 and a positive 1. Okay, and then move to the upper right. The one that people forget about most often, I've mentioned this before that, I think it's the easiest to do, but it's also the easiest to miss. And so what we can do with this one is take out a GCF. So notice the 2x and the 2 both have a 2, obviously, so you can factor that out. And then in parentheses, you'll have what's left over once you divide both those terms by 2. And then the denominator, we've got just an x plus 4. That's linear. It doesn't have a GCF, so there's really nothing we could do with that beyond that point. So once everything's factored, it's factored as fully as we can get it, we're going to cancel out all the common terms. So if you look here, we've got an x plus 1 and an x plus 1. Those will cancel out. We have an x plus 4 and an x plus 4. And then these x plus 1s could also cancel out. Because remember, this is going to become one big numerator. This would become one big denominator. So as long as you see a match, one top, one bottom, you can cancel it out, whether they're right on top of each other or if they're a diagonal like this. So notice the only thing that's left here is a 2. So after all of that factoring and canceling, we are left with just 2 is what this reduces down to. Okay, let's do another example of division, and this is one of those complex fraction examples. So you've got 4c squared minus 36 over 8c squared minus 24c, and then all over, so lots of division here. Okay, so we set that up. So really, this is like the overall numerator, and this is the overall denominator. So you're taking this piece and dividing it by this piece. So it should be set up like this. Okay, so lots of things to look at here. First of all, the division means I'm going to change this to multiplication and flip these two pieces. I also have a lot of factoring to do, so I'm going to kind of do all of that at once. So 4c squared minus 36, that's the difference of squares pattern, but I also have a GCF that I could take out. So I'm going to start with that. So I'm going to factor out a 4, and then I'm left with c squared minus 9. So it always makes things easier when you get a GCF out. You can do the same thing right underneath it. We can take a GCF from that. So 8c squared and 24c, they're both multiples of 8, and they both have a c. So I would be left with c minus 3 once I take out that GCF. And then times, remember when I change the division to multiplication, I flip these. So this piece right here is going to become my numerator. This piece also has a GCF. They both have a 2 and they both have a c. So you can take a 2c out, and that leaves me with c minus 3. And then this piece is now my denominator, because remember when I switched to multiplication, I flipped. These have a GCF of 12. So I'm left with c plus 3 there. So everything is factored down except for this. This can factor down a little bit further. That's still the difference of squares pattern. So this can factor as c plus 3, c minus 3. So I'm going to rewrite that. Okay, so now I'm going to cancel out everything I can. Kind of separate this here so we're not getting confused. So I've got c minus 3's. It's the first thing I see that I can cancel. I have a c plus 3 that can cancel here. Don't forget about these c's. These c's could cancel as well. 4 over 8 reduces down to 1/2. 2 over 12 reduces down to 1/6, or you could cancel these 2's. We've got a bunch of different options for how you reduce down. In the numerator, every single bit canceled except for this c minus 3. And then in the denominator, every single bit canceled except for this 12. Okay, remember, this c and this, this 3 and this 12 absolutely cannot cancel out. These two terms are separated by subtraction, so either the whole c minus 3 goes or none of it goes. You can't take little bits and pieces like that. So that would be your final answer for that one. Okay, so that's 8-1. You've got multiplication, division, lots of factoring and canceling that you can do. So let's take a look at 8-2. All right, with 8-2, we did addition and subtraction. So here's an example of that. Okay, so remember, in order to add or subtract two of these equations together, two of the expressions together, I should say, we've got to get it to the point where they have the same denominator. Because up above in 8-1, if you're multiplying or dividing, it doesn't matter what the denominator is, and it's the same with numbers. If you wanted to multiply two fractions together, it doesn't matter what their denominator is. Anything can multiply. But when you're adding, they have to have the exact same denominator. So like 1/2 and 1/3, you could never multiply those together because they've got different denominators. So with these, same thing, even though they're more complicated rational expressions, we do have to get the same denominator. So the first thing you always want to do with these is factor any denominator that you possibly can. So this n squared minus 9, it's the difference of squares. I can factor it to n minus 3, n plus 3. So I'm going to factor that, and then move on and do the same thing with that. That's just an n plus 3. So there's nothing that I can do to factor that any further. All right, so these two pieces, this has two different pieces. This has just one. The LCD, remember your terms can't get any smaller. They can only get bigger. So I have to have these two terms in my LCD for sure. And I have to have this in my LCD. So the LCD, I need both of these two. I need an n minus 3, I need an n plus 3. And then I also need an n plus 3, but I have one. So it would be excessive if I had two of them. So my goal is to get both of these pieces to have this denominator. This one already does. This one's missing the n minus 3 piece. So what I'm going to do is I will multiply numerator and denominator by that piece that I'm missing. Okay, so multiply that. I've got lots of simplifying to do. So this 6n piece, I'm just going to write it exactly the way it is. And then minus, now I'm going to distribute this 3. So 3n minus 9. And now I've got a matching denominator. So these pieces will be good to add together. So be careful with the subtraction. Make sure you're subtracting both of these terms. So 6n minus 3n is 3n. And then nothing minus -9, that should be plus 9. So be super careful with that. So I'm just about done. There actually is one more thing that I can do. If you notice in the numerator, it's got a GCF. They're both multiples of 3. So I can factor out a 3. That'll leave me with n plus 3. And then I have n plus 3, n minus 3 in the denominator. So because this term and this term and this term and this term are separated by multiplication, that's when I'm allowed to cancel out factors like this. So your final answer for this example would be 3 over n minus 3, and no, these 3's can't cancel. This is separated by subtraction. So your final answer would be like that. Okay, in 8-2, we also saw more complex fractions, different from the type that you had up above. So here's an example of something like that. You could have plus 3. Okay, so that is what a complex fraction looks like from 8-2. Notice the difference. This is kind of one big term up here. This is one big term. Down here, you've got 4 terms that are separated by addition and subtraction. So when you've got something like this, your goal in 8-2 is to multiply everything by the LCD. So take a look at all these denominators. Your LCD has to include all of them without including extras. So the LCD that works here, you need a 2x plus 3. You need an x plus 1. We need an x plus 1, but we're good. And same thing with the 2x plus 3. So that's our LCD. So what we're going to do is take the overall numerator, overall denominator, and multiply top and bottom by that LCD. So what ends up happening is it distributes to every single term. So I'm going to distribute my LCD to each of these 4 terms that you see in this complex fraction. Okay, so that LCD got distributed to everything, and then what's going to happen is some of my denominators will cancel out. So this 2x plus 3 and this 2x plus 3 canceled. Same with the x plus 1's right here, and the x plus 1's right here, and the 2x plus 3 is right here. Okay, so lots of distributing and simplifying to do, but notice all my denominators have canceled, so that was my goal. So I have 3 times the quantity x plus 1, so that'll be 3x plus 3. And then careful here, treat this as a minus x. Make sure you're distributing that negative. So negative x times 2x is negative 2x squared, and then negative x times 3 is negative 3x. Over, and then I'm doing the exact same thing down here. I have 2x times the quantity 2x plus 3. So when I distribute this 4x, this is what I get. And then I have plus 5 to distribute to this x plus 1. So 5x plus 5. Okay, so the only thing left to do is combine like terms. So in the numerator, my only x squared term is a negative 2x squared. These will actually cancel. 3x minus 3x, that just goes to 0. So I should have a 3. And then down here, I have a 4x squared. These two combine up to an 11x, and then I have a 5. Neither one of those factors, so that is what your final answer would look like for something else from 8-2. Okay, so we got 8-1 and 8-2. Let's move on to 8-3. 8-3, we had those, we called them reciprocal functions. And those, I think you guys were pretty much okay with. So we'll run through exactly how to do those. Okay, so we've got this. We're looking for 4 things. We need a vertical asymptote. We'll start there. Vertical asymptote, you take the denominator and set it equal to 0. So if I take x plus 2 and set it equal to 0, subtracting 2 from both sides would give me negative 2 as my vertical asymptote. Okay, so I'm going to start there. So over to negative 2, and then dot in your vertical asymptote. Okay, now your horizontal asymptote is always the number that's just hanging on the end here when you're in this form. So y equals negative 4 would be the horizontal asymptote. So I'll dot that in right there as well. So I've got my 2 asymptotes. Next thing is I'm going to take these points, 1, 1, and negative 1, negative 1. I'm going to transform them. Okay, so first thing that happens, because I have an x plus 2, I'm going to subtract 2 from all of my x values. So this becomes a negative 1, and this one becomes a negative 3. Okay, and then next for my y, I'm going to start with these values. 2 things will happen. First, I'll multiply by 3, and then subtract 4. So 1 times 3 is 3, minus 4 is negative 1. Negative 1 times 3 is negative 3, minus 4 is negative 7. So those are the 2 points that I should be plotting. So negative 1 would be right here. And then negative 3, negative 7 would be right about there. So using those 2 points, remember we kind of skim along those asymptotes. Once you hit the point, start curving and head towards the other one. That's the first piece. And then this one, we can go a little farther. Come up here. Again, once you hit that line, start curving and go along the other asymptote. So that's what the graph itself should look like. Let's talk domain and range real quick because I'm going to ask you about that. All you do with domain and range is you just exclude the values of the asymptotes. So x can't be negative 2 because of that dotted line right there. It'll never actually cross over it. And then for my range, y can't be negative 4. Same explanation, just with the horizontal asymptote. Okay, so that's 8-3. We saw those reciprocal functions. With 8-4, I'm going to walk you guys through the process, remind you of the asymptote rules that we have. So you've got a 3-step process. First step is you find what we call the zeros. You could also call them the x-intercepts. So 0 or x-intercepts, you do that by setting the numerator equal to 0. So x-intercepts are points, just coordinate points that will end up right on the x-axis. And so those will be good things to go off of when you start plotting your points. Step 2 is we're going to find our 2 different types of asymptotes. For vertical asymptotes, you set the denominator equal to 0. Okay, so just like we did in that 8-3 problem, you set the denominator equal to 0. With our horizontal asymptotes, we have 3 different rules, and it all depends on the degree of the numerator versus the denominator. Okay, so if the degree of the numerator, so we write like a of x over b of x for our function. So if the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. Doesn't mean it's 0. That means there literally isn't one. So you'll see what that would look like. If the degree of the numerator is smaller than the degree of the denominator, our horizontal asymptote is the line y equals 0. Okay, and then finally, if the degrees are equal, we say that the horizontal asymptote is, we call it the ratio of the leading coefficients. Okay, so you'll get to see an example like that next to really explain what that rule means. Okay, so the ratio of the leading coefficients. So we get those three. So sketch the x-intercepts, sketch the vertical asymptote, horizontal asymptote if there is one, and then you just use your calculator to sketch it out. Okay, and I will remind you of how to do that as well. So 2 examples that we're going to look at. First is the following function. We've got x over x plus 2. So I'm going to walk you through exactly what a test question should look like if you were doing it. So step 1 is we find our x-intercepts by taking the numerator, which is just x, and setting it equal to 0. Okay, so that means x equals 0 is our x-intercepts. For step 2, we start with the vertical asymptote. You're going to set the denominator equal to 0. So when you subtract 2 from both sides, -2 would be our vertical asymptote. So we'll be able to sketch in a dotted line there. And then for our horizontal asymptote, we look at these leading terms right here. This is a degree of 1, this is a degree of 1. So this falls into this third category. The degrees are exactly equal. 1 equals 1. So the horizontal asymptote is the ratio of what we call the leading coefficients. So here there's technically a 1 in front of the x. Also technically a 1 in front of the x here. So we take that ratio of 1 over 1. If this were a 2, it'd be 2 over 1. If this were a 4, it'd be 4 over 1. So our horizontal asymptote is just 1 over 1, which reduces down to 1. The only reason we're taking the ratio is because these degrees are the same. If the degrees weren't the same, we would have a different rule. Okay, so here's how this is going to work. Set up your coordinate system here. We start with our x-intercept. So x equals 0 is just going to be a point. The x-intercept is always just a point on your graph that the function will go through. Then go to the vertical asymptote, 2 units over here. You can dot in your vertical line right there. And then our horizontal asymptote is at 1. So 1 unit up, we can sketch this in as well. Okay, so from there, what you're going to do is just use your calculator. And you can use a graph page on your calculator to plug the function in, and then you just sketch out the shape that you should be seeing. Okay, so I'm going to go to a graph page. So in my graph page, I'm going to hit the blue key before the division key. So blue and then divide. That pops open that little graph, the function, the fraction like that. And then I'm going to put x over x plus 2 and just hit enter. And I'm going to graph exactly what I see right here. That'll tell me exactly what to sketch in, and I just mimic that graph and sketch it once I've got the asymptotes and the intercepts and everything. So go along the asymptotes through the point, and you're just imitating what you saw on that calculator screen, and it should look just like that. Okay, so that would be your final answer. So again, on the test, you need to show me all of this work, and then you can just plug the rest of it into the calculator. Let's look at one more from 8.4 so we can get a different horizontal asymptote rule and kind of a different shape in. So the next one that I want to look at from 8.4 is this. F of x equals, we've got x squared over x minus 3. Okay, so we're going to follow the exact same 3 steps. So step 1, you're still doing the x-intercept, so you take the numerator and set it equal to 0. Here when you square root, you're still going to get x equals 0. So that is your x-intercept. So we're actually going to have the same x-intercept that we had before. Step 2, you do your 2 asymptotes. So for your vertical asymptote, you take the denominator and set it equal to 0. And when we add 3 to both sides, we get 3. So that's our vertical asymptote. And then finally, for the horizontal asymptote, we take a look at the degrees. Here our degree is 2. Here our degree is technically 1. Okay, so the numerator has a larger degree. So if the numerator has a larger degree, I'm going to put that rule right back on the screen. If the numerator has a larger degree, that means there's no horizontal asymptote. Again, it doesn't mean it's 0. It means there literally isn't one. Okay, so there is no horizontal asymptote. On a test, I need you to write that down somewhere. If there isn't a horizontal asymptote, you need to make a note of that somewhere in the paper before you draw the graph. So set it up like this. We should have an x-intercept right at the origin. So that's x equals 0. We plot it as a point right there. The vertical asymptote, we go over to 3, 1, 2, 3, and then sketch in your vertical asymptote there. As of right now, that's all the information we have. We know we don't have a horizontal asymptote. So going off of this and making sure you showed me all this work, you can plug this one into your calculator as well. So same thing, blue key, then divide. So you can open up that fraction, and we're just going to type that in. Okay, so hit enter, and you'll see exactly what the graph is supposed to look like. All right, so what this one does is it almost looks linear up until it gets here, and then it goes down the vertical asymptote. Here's one thing that's really important to look at, because there's probably another shape up here, but we can't see it because we're zoomed in pretty close. So if you hit the menu key then there's this window zoom option. So hit that, and we're just going to zoom out just to see if there's anything else that we should be graphing. And you see there is something up there. Okay, so I'm going to zoom out twice. So see, there's definitely a shape up there that we could be seeing or should be graphing, but we had to zoom out a little bit to see it. All right, so keep that in mind that you might have to do a little bit of a zoom. So what our graph does, it kind of looks almost linear, hits this point, and then turns around and goes down along this, and then kind of comes along here. At some point, it's going to turn around and go back up there. So just following what I see on my graph, I'm just going to mimic that and follow along first my x-intercept and then my vertical asymptote that I see. All right, so that's 8.4. Let's look at 8.5. I'm going to write down all the different formulas that you could see, the direct variation, inverse. We've got a bunch of different options. So I'm going to write down all those, and we can go from there. And I'm just going to give you guys one example, but once you have these formulas memorized, then you should be good to go on any of those. So the first thing is I'm going to write down the direct, the formula that you'll use for direct. So direct variation, if they say that like x varies directly with y or something like that, you'd set up y1 over x1 equals y2 over x2. Okay, so this is the pair that they give you, and then usually you're trying to find either x or y. And then if they give you inverse you set up y1 times x1 equals y2 times x2. So this will help us when we go into joint and compound. If they say direct, the other variable ends up in the denominator. If they say inversely related, the other variable ends up multiplied. So when they say joints, they're normally, both of them are jointly directly affecting that variable. So for joint, you would have y over, and then they're both direct, so you'd have an x1 and then usually a z1. Same thing, whoops, that should be y1. And then y2 over x2, z2. And then for compound, they give you some sort of like mix and match. So they would say that y varies directly with x, and it varies inversely with z. So they'd set up a formula like that. And then you'd have your y2, z2. So depending on which one they say is inverse and which one is direct, you would put the inverse in the numerator and you would put the direct in the denominator. So let me just give you one example to go off of for these. Like I said, once you have these formulas memorized or written on your note card and you know how to use them, you'll be just fine. All right, so let's say we've got if A varies inversely as B, if A varies inversely as B, and A equals 12 when B equals 6, find A when B equals 8. Okay, so with this, we know it's inverse, so we're going to be using this one. So we know it's going to be A1, B1 equals A2, B2. And sometimes they'll change up the variables on you, so I just wanted to give you an example of that. So A1, B1 is this first bit right here. So 12 times 6 equals, and it says find A when B equals 8. Okay, so we just simplify that up. So on the left, 12 times 6 is 72. And then we have 8 times A. So to get A, all we need to do is divide both sides by 8. Okay, so 72 divided by 8 is 9. So that would be your answer there. So it says A varies inversely as B. And inverse means when one variable goes up, the other one goes down. So previously, A was 12 and B was 6. Since B went up, that means that A went down. Okay, so that's an inverse relationship. So again, know how to use these, and all of the formulas basically work the same. So 8.6 is our last section. We had equations and inequalities. I'm going to do an example of both. So our equation from 8.6, I will do this example. Okay, so with these, with equations, just like the stuff from 8.1, if the denominators can factor at all, you want to make sure that you're factoring them down completely. So x minus 3, there's nothing that we can do to factor that. 3, of course, is just a number. It doesn't break down. But 2x minus 6 has a GCF. Okay, so we want to take out a 2, and then you're left with an x minus 3. So we're going to rewrite my denominator in its factored form. So it would be 2, and then times x minus 3. So for the LCD, Remember, these ones, we have a different goal from the addition and subtraction. With addition and subtraction from 8, 2, our goal is for them to have the same denominator so that we can add or subtract. Our goal with these equations is to cancel out the denominator to make our equations simpler. So expressions in 8, 2, these are equations in 8, 6. So our goal is a little bit different. Again, we're trying to get the LCD to cancel all the denominators out. So if everything's going to cancel, that means that all of these pieces have to be present in my LCD. So if the x minus 3 is going to cancel, my LCD has to have an x minus 3. And if a 3 is going to cancel, my LCD has to have a 3. Remember, this 3 would not cancel this 3. You can't take little bits and pieces of factors. 2, I don't have a 2 yet, so I know my LCD is going to need one of those. And I already have an x minus 3, so that's good. So my LCD will be 6 times x minus 3. I just multiply that 3 and 2 together. So what I would do is I would take the whole equation, both sides, and multiply it by the LCD. Okay, so I'm multiplying both sides by the LCD, numerator and denominator. And remember, what ends up happening is I distribute that LCD to all the pieces. So I'm going to show you what that would look like and just color code a little bit for you. So each term is going to get multiplied by the LCD, which basically just means it distributes to everything. Okay, and then on the other side too, oops, that was a bad 3. Okay, and then this will get multiplied by 6 times x minus 3. I'm just realizing now we probably could have canceled that 2 and made things a little bit easier, but we're already on our way now. So, all right, so now our goal was to get the denominators to cancel, so let's take a look. So those x minus 3's cancel. This 3 reduces with the 6 and leaves a 2 behind. This, I guess we might as well cancel these 2's instead of canceling it with the 6. The x minus 3 will cancel. We could have also reduced the 2 and 6. The result would have been the same. So let's simplify. This first term right here, I have a 2x times 6, which leaves me with 12x, minus, here I have a 1 times 2 times x minus 3. So I'm just going to distribute that negative 2. Make sure you keep the negative with it. So 2x and then negative 2 times negative 3 would be positive 6, equals, all I have left over here is a 6. Okay, so let's clean this up. So 12x minus 2x is 10x. I can subtract the 6 from both sides, and they both cancel, leaving me with 0. So if 10x is equal to 0, I can divide both sides by 10. And of course, 0 divided by 10 just leaves me with 0. So double check, because you could have extraneous solutions. Anything that would leave the denominator as a 0 would be an extraneous solution. So if I plug in 0 here, that would be fine. That wouldn't be 0. This can't be 0. And then same thing here. If I plug in the 0, that's totally fine. So this is a valid solution. It is not extraneous. Okay, last thing I'm going to do with you guys is one of the inequalities from 8-6. Okay, so remember we had a 3-step process that we followed. So the first step with these inequalities is you write any of your domain restrictions. And so that would be anywhere where any of the denominators were equal to 0. Okay, so here if we divide both sides by 6, we end up with x equals 0. Here if we divide both sides by 3, we also end up with x equals 0. So that's a repeat. We're just going to count that domain restriction once. And then setting this denominator equal to 0, we get 9 equals 0, which is a false statement. So that's not going to give us a domain restriction. So we have the x equals 0. That's our first value that's going to appear on that number line that I'm going to set up. Second step is it says solve the related equation, which just means we're going to turn the equation, or I'm sorry, turn the inequality into an equation and solve it just like we did with that previous example. Okay, oops, I just said I was going to turn it into an equation. There we go. All right, so my denominators, 6x, that is 2 times 3 times x. And then 3x is 3 times x. And this last denominator of 9 is 3 times 3. I want to make sure that I can see the individual pieces of my denominators so that I know what my LCD should be. So remember, our goal with equations is to get all the denominators to cancel, so you have to make sure all these pieces are included so that things will cancel properly. All right, so I need a 2 and a 3 and an x from this one. I need a 3 and an x, but I'm good. I've got those covered. And then here I need a 3 and a 3. So I've got one 3, I need another 3. So that's my LCD. So this ends up being an 18x. So just like the previous example, I'm going to take both sides of my equation, and I'm going to multiply everything by 18x. So what ends up happening is that 18x will distribute. So I have 1 over 6x, and that will get multiplied by an 18x. and then I have 2 over 3x, and that will get multiplied by an 18x. And then on the other side of the equation, I have 5 over 9, and also that will get multiplied by an 18x. So if I did this right, my denominators should cancel. And so here, 6x reduces with 18x and just leaves me with a 3 behind. The x's would totally cancel, but the 18 over 6 would be 3. Same thing here, the x's totally cancel. The 18 over 3 leaves me with 6. And here, the 9 and 18 reduce down to 2. The x doesn't cancel, so the x would still be there. So this term right here, all I have left is 1 times 3 plus, and all this right here, I just have 2 times 6 equals, and here I have 5 times 2, which is 10 times x, so 10x over here. So just to finish this off, the 3 and 12 gives me 15, and then here when I divide by 10, 15 divided by 10 is 1.5. Okay, so these are not my answers. These are the numbers that are going to mark up my number line. So my third and final step is I'm going to set up, well, I guess 3 is just setting up the number line, 4 is the test values. So I divide up a number line using those values that I came up with for step 1 and step 2. And then the final thing I'm going to do, so this is my step 4, is I'm doing all my test values. Okay, so different test values. So in this region right here, let's go with the -1. So anything you want, any number at all, could be any negative number. Here in between 0 and 1.5, let's just keep it easy with 1. And then anything bigger than 1.5, let's go with 8. Why not? So anything you want in these regions to test out. So I will remind you on your calculator of how to test that out. So what you do, you should be in a calculator page, and you pick your first test value, type it in, and then store it. So hit the blue key and then the variable key, and you can store that in as x or whatever your variable is. So now that that's stored, we're now going to go up to the original inequality and type that in. So a fraction of 1 over 6x plus another fraction of 2 over 3x, and then less than. Remember, for these you go into the equal sign, hit the control first, and then you can grab whatever inequality you need. And one last fraction for 5 over 9. So that's true. Okay, so when I tested something in this region right here, it came out true, so I'm going to put a big T there. And then something between 0 and 1.5, I'm going with 1. You can choose whatever you want. Store that in as x instead, and then just arrow up a few times. Get this highlighted, enter once to paste it, enter again to test, and that one's false. So in this region, what I tested came out false. If you tested something different in that region, I promise it would also come out false. And then finally, something bigger than 1.5, I'm going with 8. You can go with anything bigger than 1.5. And one last time, arrow up a handful of times till it's highlighted. Enter once to paste it, and enter again to test that one. That region turns out true. Okay, so that is true. So for my final answer, I should be naming these inequalities. So this one right here are all the x values that are less than 0. Okay, and then you say or. When they're separated by two different pieces like that, you say or. And then this piece right here would be any x value that's greater than 1.5. So 0 is a domain restriction. That can't possibly be or equal to. This, it would be or equal to if the original was or equal to, but it's not. So this one isn't either. So this would be your final answer for that inequality. All right, so that is all of Chapter 8. I hope that that was helpful.